Well, good morning, afternoon, or evening for everybody who's joined in. Thank you so far for those who are patiently waiting for this webinar to begin. My name is Brian Benish. I'm the Assistant Director here with DSIAC. And I'm just going to quickly give an introduction to our organization for those who aren't aware. And then I will give the balance of the time over to Pat Buckley for his presentation here on modeling reactive metal fragment effects in endgame simulations. So just a quick overview on DSIAC, the Defense Systems Information Analysis Center. We are a DoD entity under DTIC, the Defense Technical Information Center. That is essentially the DoD's technical library that has millions and millions of technical reports that are produced, at least in part, by some government funding. In support of the DoD community, DTIC has stood up the IACs, these information analysis centers. We are one of 3 of those under DTIC right now. And we exist to help those in the DoD research and engineering community find the information they need to help get a head start on whatever technical work they're performing. So we have technical folks on staff to help find information on any defense system technical topic of interest you might have. I would encourage you to go to our website, DSIAC.org, poke around, see what you can find. We've got a lot of great information there, but most importantly, reach out to us, contact us to help you out to find whatever you might need to get started on your work. One method we execute in performing this work to create an awareness of work that's out there is these webinars. We host monthly webinars, kind of actually been at a pace of maybe every other week more recently, but these webinars are technical presentations intended to give you all, and those in the DoD research and engineering community, give you all an understanding of what work is being performed out there so that you can help have that awareness, maybe not repeat work that's being done or has already been done. Maybe you could build on the work or collaborate with those who are presenting or taking part in these webinars. So this is just one way that we're going to do that. So that's just a quick overview of DSIAC. Again, I'd encourage you to go to the website. If you want to contact me, you should be able to find my information online somewhere, Brian Benish. Email simply brian.benish@dsiac.org. And so just a couple quick logistics for the webinar. For those who are joined in on the web platform, you should be able to see the slides, and you'll be able to see them as we progress through and as Pat presents them. You will notice if you are joined on the web platform, there is a question dialog box should be at the top middle of your screen. At any time during the presentation, if you have a question, please enter it there. We will field the Q&A portion at the end, and we'll go through them in order that they are received, so please enter them there. I want to distinguish that from the chat box. There's a attendee and presenter chat box on the left-hand side of the screen. Again, that's not for questions, that's more just general chat. We'll keep an eye on it. If someone does accidentally put a question in there, we'll make sure we throw it in the Q&A portion. But again, the formal question should be asked at the top of the screen, little dialog box. It says view audience questions, and you can enter your question from there. For those who are simply dialed in, or if you have any technical issues at any time during this presentation, you can dial in. The dial information is available. Should be on the website to get to it, or in the invite that you would have received. And the PDF of the presentation, if you want to follow along with the slides, is available on the webinar's webpage on our website. So you can go there, download the PDF, and follow along with the presentation. Okay. Final note: this webinar presentation is being recorded, will be recorded, and will be made available. So if you do have any issues, we'll make sure we share out the link for that later, and you can listen in on it and watch it at your own leisure. So that is a lot of overview. Now I want to hand it over to Pat Buckley for his presentation. Pat, all yours.
All right, thanks, Brian. I'm scrolling through the list of attendees on my screen here, and I see some familiar names and some unfamiliar names. So thank you, everybody, for taking the time to listen. I am an Endgame simulation developer and have been since 1968 when I was a sophomore in college. My introduction to reactive lethal mechanisms goes way back to 1977 when I worked at New Mexico Tech for EMRTC, what's now called EMRTC. And we were doing test work for Quantic Industries, a gentleman named Herb Weintraub. And they were promoting a substance called QAZ. And the QAZ, the Z part of QAZ was zirconium. And you could coat munitions with QAZ and it would add an incendiary effect to their kinetic effects. And I've kept an on and off interest in this area since then, and just recently got interested in it again. Up until this point in time, endgame codes, computers really haven't been powerful enough to do a whole lot with sophisticated mechanisms in endgames, but they are now. So this is an example of that. All right, so let's just jump right into it here. If I could find the slide thingy. Oh, there we go. All right, so reactive metal fragments. These are mixtures of metal powders pressed and sintered into solid fragments. And so they're engineered materials. And one example is Teflon, aluminum, and tungsten, which can be pressed into materials that have a density of steel. I'm not promoting that particular material as the best one or the answer. There's a lot of work going on in that area. This is just one example. Generally, normally, these things are benign, but if you heat them up enough, they will react very violently. And one way to get them to react is to shoot them into something, and the ballistic impact heating triggers the chemical reaction. The energy released per unit mass, if it goes to completion, can exceed that of TNT, so they can produce some pretty exciting effects. So reactive metal fragments then have the potential for combining kinetic energy effects with a chemical energy release and thereby produce more damage. So this is an example of a reactive metal, one example of a reactive metal impact. And this is a paper presented in the International Journal of Multiphysics by these Chinese researchers. And this is a fairly typical experiment where you have a striker plate and a witness plate downstream from that, and you fire reactive metal material into this. In this case, there were about 70 grains, 4-gram projectiles, and they were impacting at around 1,250 meters per second. You can see from this picture over here on the lower left, you get this tremendous luminous effect. So there's a lot going on here. And in fact, this test blew a big hole in the witness plate, the aluminum plate downstream, as you can see here. The inert fragment will just produce a nice round hole. These are not to the same scale, of course. This is a scale underneath this one and underneath this one. This is about 4 inches wide or so. So there's a lot of damage done to this thing. And on the face of it, the reactive metal fragment does a lot more damage to this witness plate than an inert fragment. But interestingly, if you were a vulnerable component that happened to be in the neighborhood here, shot line's over here someplace, you can be off the shot line and all this damage zone around there might affect you as well. So that brings in the possibility of damaging things that are not on the shot line. And that's not something that's done in endgame codes currently. So this little cartoon shows that. There's additional damage mechanisms to be modeled for reactive metal fragments in the endgame code. The first is a reactive metal fragment, because of the chemical release, probably is more lethal against vulnerable components. That has to be accounted for somehow. And then there are also shot lines that miss a vulnerable component and yet damage it because of the energy release in the neighborhood. So the question is how to model these things in the endgame simulation. So the fundamental thing in an endgame simulation is the modeling of individual shot lines. In the case of inert fragments, it's fairly straightforward. They will impact things, reduce mass and speed, impact another thing, reduce the impact speed more, and eventually they'll stop or exit the target. So the penetration modeling is done with well-established algorithms. To mention three are FATEPEN, the JTCG handbook equations, and ProjPen. All three of these are basically empirical techniques fit to test data. And there's maybe 1,400 tests or so that go into this. And these are well accepted as the way to do this. If this fragment hits this thing and this thing is a vulnerable component, then it will have associated with it a fragility function that returns the probability of damaging that thing as a function of impact speed for different fragment masses. So the fragility function is typically a function of mass and velocity. You give it the impact mass and speed, and it returns a damage probability. So similar things have to be done for reactive metal fragments. And that's problematic because these are not steel or tungsten. They're all kinds of materials. So the question is, how do you model the penetration of this material as it works its way through a target? And there are dozens of these materials that have been considered and are being considered. And 1,400 tests up here just do steel and tungsten. So you're not going to do 1,400 tests for 40 materials. So this could be a problem. So penetration modeling is one thing. The second is an algorithm for energy deposition. So as these fragments hit things, how much energy are they depositing as they work their way through the target? And then how to modify fragility functions to include the effects of the chemical energy in addition to the kinetic energy. And then, of course, how to model indirect damage altogether is something that's not done. That's something that's not done at all in current endgame codes. Okay, so I am a physicist by training. So my first inclination is to, as the old joke says, consider the horse a sphere. So we'll simplify things considerably just to get started here. So the penetration algorithm, I'm going to assume, and I've included this in an endgame code. The penetration algorithm, I'm going to assume it gets through the skin intact. Then I'm going to further assume whatever it hits next is going to stop it. And all the energy is going to be released at that point. And that's the energy deposition algorithm. It all happens at the second impact. Fragility function modification, I'm going to assume that these reactive fragments have a pK of 1. Otherwise, why use the stuff? And I know that's an optimistic assumption, but that's okay. Let's just see where that leads. In the indirect damage model, I'm going to implement a lethal radius model. And yeah, I know that some of them break up, some of them don't break up, Dan. So the lethal radius model for off-shot line effects is fairly simple. So you have an impact, and there's a lethal radius associated with that. And if you're a wire bundle, for example, inside that lethal radius, you'll be killed. If you're outside that lethal radius, you won't be killed. And I'm going to modify that. And I'm doing it that way because reactive metal fragments, to me, look like a mini explosion. And we've used lethal radius for blast before, so this was the first thing to try. I modified that a little bit by having it 1 out to the lethal radius and go down to 0 at 1.5 times the lethal radius. All right, so how to determine if a vulnerable component is inside the lethal radius? Well, this is a technical problem in the endgame itself. And so I'm doing the simplest possible thing. I'm going to cover the surface of each vulnerable component with points. And then I'm going to determine which of those points have a direct line of sight to the reaction point. Then I'll calculate the distance to all those with a direct line of sight, and then test them versus the lethal radius. And this algorithm works because I'm keeping the points in the KD tree, which is a data structure that lends itself to very fast radius search. And your cell phone has a KD tree lurking in it somewhere. And so when you ask to show me all the pizza joints within 2 miles of me, a KD tree is invoked to give you that map. So surface point creation, the first step in this process. This is a generic drone target, unclassified, 10 feet long or so, has internal vulnerable components of various kinds. Covering all those components with points spaced 2 millimeters apart ends up with 1 million points. Takes about 0.2 of a second. That's multi-threaded. So it doesn't take long, and this is a pre-calculation step anyway. You only have to do this once at the start of the endgame. And if you focus in on the central area here where a lot of things come together, you can kind of see the points. Getting the points evenly spaced exactly evenly spaced is a difficult thing, and there are many PhD dissertations that have been given to that. I chose a pretty simple algorithm, and they're more or less evenly spaced. So the shot line processing steps here are, this is a shot line going through the front of the fuselage. I removed the skin of the fuselage so you can see the shot line as it goes through the target. And enters here, hits a bulkhead here, and goes on out of the target. This red point here should actually be up here. All the blue points are the surface points on the vulnerable components. Invoking the KD tree radius search, how many points are within 1.5 times 2.54 centimeters of me? 2.54 centimeters is my assumed lethal radius here. So you can see the KD tree search reduces this huge thing down to just a few points. And then I ray trace from the reaction point to each one of these to eliminate the ones that have something in the way. And that would be the ones on the back side of this cable bundle here. And then it's a matter of those left computing the distance map to them. And if you rotate this thing around, you can see the hit points over here now. You can see a color-coded distance map. So in the center here, it's probably around 2.54 centimeters and then down to 0 at the edges. So those can be compared to the lethal radius and determine the damage probability. All right, so what does this look like in an actual example endgame? And I'm choosing a simple one here. I'm looking at a 40 millimeter grenade projectile that is a high explosive fragmentation projectile that is command detonated. And it can generate about 120 fragments, maybe 20 grains each, 4,000 foot per second ejection speed or so, 20 degree side spray, standard stuff for a projectile like this. And we'll use the drone as a target. The endgame code is a point burst code. So at each burst point, we generate sets of shot lines randomized and see what they do against the target, and then repeat that 20 times and average the PKs for everything. standard point burst stuff. To generate a set of burst points for an actual endgame, I'm assuming that the encounter is head-on, so we're just shooting straight at it. And the radial dispersion of the burst points is a Rayleigh distribution with a half-meter CEP. So this is 1,000 burst points generated with a half-meter CEP. In the other dimension, this is a command-detonated projectile, and it's given a detonation time, but there are errors associated with that. And they're, typically plus or minus 1.5 milliseconds, randomly distributed in there. So that spreads the burst points out in the other direction. So this is the cloud of burst points we're analyzing. If we assume, and then the target has each component has a fragility function, and the fragility functions I'm using are kind of a generic set that I've accumulated over 40 years of being in the business. They're all unclassified, of course, and they may not be the latest and greatest thing, but they're reasonable. If we do this set of burst points with that projectile and sorry, I'm looking at the messages there, and assume the fragments are steel, then we get a PK of 0.5. And PK in this case is probability of killing any single component. There is no fault tree per se here. If, on the other hand, we assume that the reactive metal fragments have a pKh of 1 on vulnerable components, and furthermore have a lethal radius of 1 inch, 2.54 centimeters, then the numbers jump to 0.91. And, I've been doing endgame work for a long time, and it's really hard to move these numbers around. And I didn't expect this. This is a huge increase in PK. And admittedly, the assumptions here might be optimistic, but it's encouraging if you're a reactive metals person that optimistic assumptions led to very large increases in PK. So to break that down a little bit, the steel fragments are KE effect only, of course, that's a PK of 0.5. If I set the lethal radius to 0, then all you're going to see is the increased lethality of the fragments that hit vulnerable components directly. And that jumps from 0.5 to 0.7. And then if you add in the indirect effects with the lethal radius, that jumps to 0.9. Second analysis involves a truck, and you're trying to stop the truck from moving, so the burst points are set above the projectiles are set to go off above the hood. And this is another cloud of burst points with a half-meter CEP. This is inert fragments. This is reactive fragments. Again, very large increase in PK. So the point of this talk is not necessarily to get solid numbers, but to look at what the implications are in the end game. And one thing I wanted to know for sure is how long are the run times going to be here? If it takes forever to run these things, it's not going to do much good. So this is a comparison of the run times for the inert to the reactive. For the drone, it was 0.7 for inert, and reactive is 1.8. This is 1,000 burst points, 20 Monte Carlo samples at each one, 120 fragments. So it's 2 million shot lines total in the whole analysis. It's pretty interesting that, 2 million shot lines, you can do that in 0.7 seconds. That's pretty good. So this isn't too bad an increase, and the truck has the same sort of thing, maybe 2 times the amount of time. So it's practical to do. Now this code that I put it in Turbo PK is fully threaded, and the calculation of the points are also fully threaded, and the KD tree is fast. So calculation speed doesn't seem to be a problem here. The KD tree is one way to do this. There are other data structures that are useful too. This is a 2D representation of the KD tree. And what KD trees try to do is subdivide into rectangles that are controlled by the by the distribution of the points. An alternative is a uniform grid where the the actual rectangles or cubes are the same size and you put the points in them. I looked at this because this is a simpler algorithm than the KD tree, and it would be simpler to debug it, and you're going to have to debug it at some point, trust me. And it turns out the uniform grid was actually faster than the KD tree. And there are all kinds of other algorithms here for radius search, R trees, bounding volume hierarchies, space filling curves, Morton curves, Hilbert curves, and so forth. So this is a rich playground of things if you're into that. A more complicated model, yeah, I don't want to take this too far, but I did add some complications to it, where I just decided to treat the reactive metal fragments as steel using the penetration equations for steel, but increasing the ballistic limit by a percentage that the user can control. The energy deposition algorithm just assumes that the energy deposited is proportional linearly to the kinetic energy loss in the projectile. Likewise, the fragility function pK increase is linearly adjusted by the kinetic energy loss. The idea there being that whatever kinetic energy is lost in an impact goes into the chemical energy. I realize that's kind of a base assumption. In the indirect damage model, I just assume the lethal radius is linearly proportional to the KE loss too. So in this way, you can spread the reaction and the material out as you go through the target. And in this code, in this case, I just assumed the ballistic impact or the ballistic limit increase was 50%. Yeah, I know linear and nonlinear. I get that. The lethal radius is 2.54 centimeters at 1,400 meters per second and 1/10 of a centimeter at 800, and varies linearly in between. The lethality on components that you hit is increased by 50% for 1,400 meters per second and no percent at 800. And you can play with this all you want. And that drops the pK numbers to 0.88, so not too much. So what I've done here is I've modified an endgame code in a particular way to treat what I think some of the important things are for reactive metal fragments. It shows a large potential gain in pK for RMF. It's fast. The KD tree radius search data structures are the key here. And I realize there's lots of assumptions that went into this, and those would have to be examined. By the way, this was unsponsored work, so I did this all on my own. There's plenty of work to do here still. You could have per component lethal radii. Penetration model for RMF, as I said, is problematic. I'm sure there's probably work going on there that I'm unaware of. Likewise, the energy deposition model for the RMF is problematic. And one question I had was just countermeasures. This came from the point of view of us using this as a weapon, but what about somebody else using this as a weapon against us? And I just raised that as a curiosity. And there are other things too. So that's the end of my presentation. So I guess we'll entertain questions. I saw a number of comments go by.
Very good. Thanks, Pat. Yep. I have been collecting some questions, and I will just take a moment here to remind everybody who's in the web platform version of this. There is a View Audience Questions dialog box at the top of your screen. That's where you can go to enter your question, click Add New Question, type it in, and off you go. So we've got a couple in queue, and we'll work down from there. But as I'm speaking, and anytime if you have a question, you guys can please enter it in there, and then we'll address them as we go. Okay, so let me play these, and we'll go from there. So first question, and I think we have a couple that are in this effect here, is what testing is being completed to validate these simulations that you've shown?
That would be none. This, as I said, this work was not sponsored by anybody. This was something I have a personal interest in, so I did it on my own initiative. Clearly, a lot of testing would have to be done to validate or even design the algorithms that need to go into an endgame code. I would love to see testing. And if I was king for a day, what I would do is gather up typical vulnerable components, hydraulic lines, wire bundles, black boxes, actuators, fuel lines, and shoot candidate materials at them, inside targets and outside targets, see what happens. And that would lead you to model development. But no, nothing that I know of. Somebody probably is doing testing. I'm just not aware of it.
All right, very good. Thanks, Pat. Next question. Can you please explain why kinetic energy only increased as it should decrease due to the worse penetration of the RMF?
Why KE only increased as it should decrease due to the worse penetration of the RMF. Well, the KE only is the inert fragment number. And I don't think, unless I made a mistake on the slide, I don't think it increased. It was 0.51 for the drone target. Does that answer your question, Dan? I'm not quite sure.
And unfortunately, I mean, you could reply over chat here, Dan, but microphones are by default muted, so I won't be able to hear him respond. But yeah, if you have a comment or response to that, Dan, we can entertain that. But we'll jump to the next question in the meantime. All right. Again, same kind of question. Has anything in this methodology been verified or validated?
No.
Okay. Just double checking. Okay. All right. Next question. Is a 1-inch lethal radius for a 20 grain fragment realistic for current reactive materials? That seems to be where the value is.
I don't know. I actually attended a test firing of some of this material at EMRTC, and it was less than a 20 grain fragment, and it was at 3,000 feet per second. And I can tell you this much: I would not have wanted to have been standing anywhere near it when it hit something. So I don't know. 1 inch. I mean, one of the reasons I did this was to allow you to play with that number and see what matters. You know, if a lethal radius of 1 inch doesn't make any difference, then, you know, who cares? If it has to be 1 meter, it's not going to work. So I don't know. I don't know that it is realistic or not. It seemed to me to be a reasonable place to at least start.
Okay, no, fair enough. That's good. All right, next question here. Is the assumption that RM is a mini explosion or similar to it? Is that a fair assumption? And then there's the added comment that it seems to have been debunked years ago. I'm not sure, what that's referencing, but I'll just let you comment on that, Pat.
Yeah, well, that may have been a poor choice of words. The lethal radius works for things that show a sharp fall off as a function of radius. And I don't know that that's the case necessarily for reactive material, but if you're dealing with something that raises pressure and that expands out as a wave, that's probably going to go down as 1 over r squared or 1 over r cubed. And so that you would see a pretty steep curve there. So that's my real defense for using the lethal radius, but also its lethal radius is simple to implement. And did I mention this was unsponsored? So I wasn't interested in spending too much time on it. Next question.
You get what you pay for, right?
Well, no, that's not necessarily true. Sometimes you get a lot more than what you paid for.
That's what I was going to say. All right, in this case, you get a lot more here, right? All right, let's jump to the next one here. Well, same question here. Not been validated against any test.
No, it hasn't been.
All right, next question. How does RMF penetration compare with steel penetration?
Well, there's lots of different RMFs. I mean, the original RMF work at Dahlgren was aluminum powder and Teflon powder, so they were fairly light. They weren't very dense and weren't very strong, so they didn't penetrate real well. But there's at least one paper in the open literature, again by Chinese authors, where they claim that for some of these denser materials, this Teflon aluminum tungsten material that I referenced has the density of steel. And they did exactly one test where they measured the residual speed and mass of the fragment, and it looked like the ballistic limit was increased by 30% for an RMF that has the density of steel versus a hard steel fragment. So that's just one data point.
Okay, no, that's good. All right. Next question. Can you take an FEA model as a recipient target?
Yes. We are big believers in stereolithography models. And we, in fact, when we build a geometry model, which we do a lot of for laser work, not for this work, we use SolidWorks because it's a pretty good CAD code. And then we export the geometry as stereolithography components, triangles, basically triangles. And then in lethality code, that's what we use. We use the geometry as stereolithography elements, essentially. So yeah, we can use an FEA model.
Good, that's great. All right. Why are the nose hits red for uniform and blue? Oh, for uniform and blue for KD tree. Slide 16.
Well, let's see.
Want me to jump out of Q&A so you can go to 16?
No, I know what she's talking about. That's a good question. They probably should be red for both. And those are direct hits, is what it comes down to. They should either be blue for both or red for both. And that's an oversight on my part. If I remember right, That's maybe as many as 10% of them, something like that.
Okay.
Okay, Dan. Message from Dan. What kill level? Not
Let me.
any particular kill level. Okay, can AI and deep learning have a space in this modeling technique? Oh,
Hey,
absolutely. Yeah, absolutely. Um, and generally speaking, I mean, endgame codes generate one heck of a lot of information. You know, all these hits all over the place and the residual masses and speeds and combinations of things that get hit, and we throw away most of it. You know, so we generate this huge amount of information, and we don't do much with a lot of it. Um, but it's possible that by saving all of it, you could use something like AI and deep learning and make something out of it that we're not now. So yeah, I think it could. It could have a application generally, and in this modeling technique especially. Good question.
yeah, another thing to add to the future work list. All right, next question. Is this technology applicable to minimizing collateral damage? Fragment reduces its weight as it goes through the air.
Uh, hmm. I suppose um, that's an effect that would have to be engineered into the material itself. I have seen work. I mean, I'm familiar with the work done at China Lake on fragments that do just exactly that for application to uh, active protection system projectiles. And you know, we do calculate drag. Uh, we do calculate drag in this code. So you know, the distance the fragment has to travel is taken into account there, and it could be used to shed weight before it gets to the target. I don't do that, but it could be made to do that.
Okay, perfect. All right, next question here. How do you anticipate quantifying energy from RM?
Well, uh, I don't. I mean, I'm an endgame analyst and not a material scientist, but the work that's been done, most of the work I've seen has been done in these so-called PIG um, blast chambers, basically, where you fire reactive metal into at an anvil inside an enclosed volume and measure the pressure rise versus time and temperature rise versus time, and that can give you an energy release versus time history.
Perfect. Okay.
But I don't, I'm not doing any of that work actively myself.
Hmm. Okay. All right. Next question: is friction taken into the loss of energy?
No.
Easy answer. All right. Moving on. Are you aware of NSWC Dahlgren's ETB that has these capabilities and more?
Vaguely. Um, I, what, you know, my approach to this was to take a clean sheet of paper, and I've been doing this work for a long time, and I didn't want to just me to it with what somebody else has done. I am aware that NSWC, and I know about NSWC's ETB, and I know that they've been working on this, and I'm you know, I'm sure their work is very good, and I would be interested in knowing more about it. Um, but I don't know. Can I get ETB and exercise it, or is that not possible?
Yeah, Dan, I might get with you offline, see if maybe we could set up a presentation here on ETB and that capability as well. That would be great to make sure we share that information out to the community.
Yeah, I agree. I'd be very interested to know what they've done.
All right, next question. Have you given any thought to the particle burn model?
Just a little bit. The people at the Naval Postgraduate School who work for Dr. Hooper do have a burn model and a pressure. They actually have a reaction model that's expressed as a 1D differential equation model. And implementing something like that in an endgame code would definitely be possible. We do something like that with our laser code. We have a 1D differential equation solver for heat flow. And it turns out that's practical to do. But yes, I've just given minimal thought to it.
Okay. All right, next question. What tests do you think would provide the most bang for the buck in validating the various assumptions baked into your approach? You were king for the day.
Bang for the bunk or the buck? Right. Well, that's a good question. One of the uses of in-game codes can be to guide testing. So you would run the code and see what it would think would be the biggest payoff. And I'd have to think about that. Definitely component testing. And generally speaking, you want to shoot at the biggest things because they're the ones you're going to hit the most. I'd have to give some thought to that. Good question.
Okay. Is the model accounting for the difference in reaction extent associated with impact on different materials?
Only to the extent that the penetration equations, if it's valid at all to use the steel penetration equations modifying the ballistic limit, if that's valid at all, then that does take into account impact on different material types. The penetration equations do. So
Okay.
yeah, it does indirectly do that.
Good. All right, next question. Okay, you mentioned, could you email out the Chinese reference paper on RMF penetration?
I don't know that I can distribute that paper, but this slide gives you the reference, and if you Google for that, which is what I ended up doing, you can find a link to download it.
That's right. It was slide 3 or something, I believe.
It's slide 3. Yes.
Yeah. Okay.
Yeah, the reference, the full reference is there.
Exactly.
By the way, if you, there's all kinds of literature in the open literature about reactive metal fragments. Most of it not done by us. Most of it done by others.
Yep. All right. Next question. How was the RMF collision and chemical reaction modeled?
Well, there was no direct modeling of the chemical reaction per se. It was just assumed that there would be one, and that would result in a certain lethal radius. So surrounding the point where that reaction occurred due to increase of temperature and pressure. But there was no chemical reaction modeled in that. Now, probably the shockwave propagation and compression of these materials could be used to estimate the heating of the material, and that could be used to somehow model a chemical reaction. But I didn't do that. That's a good question. You could do something like that.
All right. Good. All right. Next questions. Next question. So if AI and deep learning is useful, then you will need a lot of results. Using a high-resolution particle-based FE solver, which tracks fragments, would be useful to generate the data. I kind of landed on the question at the end, but the
Yeah,
question being, would a high resolution particle based FE solver that tracks fragments, would that be useful for AI or deep
absolutely.
learning type? Okay.
Yeah, absolutely. Um, and and that's actually the kind of the modern way algorithms are generated for in-game codes is done in conjunction with a hydrocode or finite element code in experiments. I mean, the finite element codes produce a lot of information, and yeah, that would be very very useful. An example, by the way, is I don't know, 20 years ago, Kevin McArdle and my colleague Kevin McArdle at Eglin Air Force Base, or Service Engineering at Eglin, had submitted a proposal for the Air Force to do something like that to supplement the penetration equations for inert fragments, where there are 55 materials that are handled by Covart and other endgame codes, but there's only test data against a handful of materials. So our proposal was to use a hydrocode run automatically, as it were, for weeks on end to generate synthetic experimental data for materials that hadn't had test data. And I realize some of the phenomena aren't going to be modeled correctly, but using all those results then to uh, augment the actual experimental data to do a better fit for materials that hadn't been tested. So yeah, using a finite element, we're big believers in doing that kind of thing.
Mm-hmm. Very good. Okay. Is this technique applicable for implementation in AGEM?
Sure, I don't see why not. I mean, the you know, if there's anything, I guess, of real interest to endgame coders there, people actually write endgame codes, is the concept of doing a distance mapping to nearby vulnerable components to reaction points or other things. And by the way, Kevin McArdle has suggested that this same technique could be used for modeling fragments as 3D objects and not infinitesimal shot lines, and seeing what they're near. So yeah, this could be done in AGEM.
Okay, perfect. Yep, and just to make everyone aware, HM, the Advanced Joint Effectiveness Model, it's a survivability, lethality, vulnerability simulation code. All right, next question. So how does Turbo PK compare to other in-game simulations developed by, well, DSIAC developed this simulation or Turbo PK, but we distribute it on behalf of those who have developed it, known it. But in any case, how does Turbo PK compare to the other endgame simulations like VTK?
Well, that's a pretty complicated question, of course, but the vulnerability parts of Endgame are the penetration equations, the fragility functions, and the fault trees. The rest of it's ray tracing and beam counting. And so in Turbo PK, we tried to stick to accepted standards for those things. And it uses the JTCG penetration equations handbook for penetration equations, for example. It could also use FATEPIN. It could also use ProjPIN. We don't do that right now because that requires licensing of those things by the users and so forth. But there's no reason it couldn't be used. Fragility functions are standard bivariate mass and velocity, and fault trees are standard covert 4 fault trees. The Turbo PK is well described in Morris Drill's book on advanced weaponeering. The latest edition is the third edition, and the second volume of that has an entire chapter about Turbo PK, and it explains pretty well what it does. And it's not meant to compete with other in-game simulations per se. It has things in it you don't find in some other things. For example, there's a warhead design capability directly in Turbo PK. So you can design warheads and go back and forth, um, go back and forth between warhead design and lethality. And yeah, I saw the comment that went by Tom there. Um, I don't think of it as competing directly with it, actually. Turbo PK is really fast, for one thing. But okay, is it releasable? Yeah, it is. You would contact me or my boss, Matt Perini, or somebody at Service Engineering and ask for um, a beta user copy of it, and we'll take it from there.
All right, very good. Thanks. So we've got a few more minutes. I want to kind of close out here about 1 o'clock. 7 questions I've got in the queue. So let's see how far we can get. All right, you mentioned incendiary effects of RM in the early part of the talk. Is this incorporated in your modeling, or could it be?
Anything that can be modeled as a lethal radius effect can be modeled. Anything that requires distance mapping to nearby component surfaces can be modeled. So if incendiary effects need those, which they would, then in theory it could be.
Okay, good. All right, let's keep moving. Next question. Why go through surface point generation as opposed to using the full surface for impact measurement?
Well, that's a good question. Fundamentally, what you want to know is what's the point of closest approach between the reaction point and a nearby surface, and something that's visible to you. I don't know. I chose points because they're really simple, and if you have a better method for doing it, I'd be interested in hearing about it.
Okay.
Fast. It's very fast.
All right. How much time does it take for for somebody, I suppose, with an average IQ to learn this software? How user friendly is it?
It's pretty user friendly. It's typically when I sit down with somebody and walk them through it, they could be doing useful stuff in an hour.
Okay, good. All right, next question.
Rod Dabeline just made a nice message there. Even he can do it. Rod uses Turbo PK occasionally. That's not the knock on Rod. It's pretty easy to use.
Okay. Yeah, and a good point here. This is kind of a question, more comment here about, yes, this is public forum. This is distribution A level. So everything should be kept to that. Discussing just simply the overview of some of these lethality codes are distro A, but if we started getting into the nitty-gritties of how they work and some of the more controlled information within them, that would be concerning. But yes, we're keeping this at distro A level, so important to kind of remind us here. All right, next question. Has functional data analysis tools such as SAS, JMP been used for these penetration time domain trajectories? There is good precedence from the chem biodispersion sims at the Army's ECBC.
I have not. I can well imagine that there's been a lot of work done on dispersion simulation of chemicals or anything, and I have not done any of that. But that's a good recommendation for somebody to look into that.
Okay, great. Okay, I think this is our last question next. Don't most RMs require some sort of minimum initiation event, either pressure shock or temperature friction? Is this accounted for? And if not, how would you approach it?
Yes, of course. Yeah, there is a minimum impact pressure shock. There's a minimum energy input required into this stuff to get it to react. And in this simple model I've done is the reaction extent is modeled linearly with a minimum speed of, in this case, in the example case, 800 meters per second, and maximum effect at 1400 meters per second. So it allows you to specify a minimum impact speed. And I just did a linear. I'm not saying it should be linear physically. It's just what I did.
Mm-hmm. Okay. So that'll round out our Q&A. Just a kind of a final comment, a couple comments here. Again, this is being recorded. We'll make this available. Kind of disclaimer to the whole thing probably should have been mentioned up front. Of course, this is a not necessarily any government endorsement here by being a presentation from or hosted by DSIAC. This is our attempt, DSIAC's attempt at featuring work that's kind of being done by those in the DoD research engineering community to make sure there's an awareness. So this is not necessarily an endorsement, not intended to be anything competitive towards other solutions that are out there. This is simply meant to create an awareness of work that is being done, perhaps spawn some collaborative opportunities, something that can grow from here. So please keep that in mind. And then if there are any interests, though, in this particular software solution that Pat has discussed, his contact information was on the front slide. Simply email him, call him, and he can kind of take it from there to see what we can do to get you using this or answer any more detailed questions you might have. So that said, I think we're kind of going to close out from here. Thank you, everybody who has stuck it out this whole time. I appreciate it. And thanks for being with us. Thank you, Pat.
Yeah, you're welcome.
All right.